Yeah, so today we are going to study permutations. So yeah, these are one of the most fundamental objects in combinatorics, and there are really a lot of properties that you can study on permutations. Permutations are actually a very active area in enumerative combinatorics, so we can actually spend just a whole semester studying just permutations only. But of course, it's a kind of vast area, so we will only cover very basic things that we will need later. So first, definition. I'm sure that you all know this definition, but let me define it anyway. A permutation on n. This is a set of integers 1 up to n that I used last time. Is nothing but a bijection. Say a pi from n to itself. Bijection means a function, a one-to-one and onto function. So it has an inverse. And if you collect all the permutations on n, we can define a group structure. So that's because we can combine two functions, compose two functions. So the symmetric group, which I write this notation, so math frac. So basically S with a strange font. This is the group of all permutations on n. So because it's a group, we have to define the multiplication with multiplication. So pi sigma is defined to be composition of functions, so composition of functions. Okay, so we can compose two functions, and it's still a bijection, so yeah, it's a group. And of course, that means this is a permutation, so it sends I to pi of sigma of I. So it's a map from n to n. All right, and we will write. There are several notations that we can use to represent permutation. So pi is, we will write this as a word like this: pi 1, pi 2, pi n, where pi I is the image of pi, image of I under pi. All right, and this is called one-line notation for a permutation pi, and there's a two-line notation. Two-line notation means we write pi is really the same, except we write this like a array. So in the first row we have n numbers 1 up to n in this order, and here we write the image of 1, image of 2, etc. So these all mean the same thing. So pi permutation can be considered as a function or bijection, or a word like this, or an array like this. So for example, let me give you a simple example. Pi in the permutation symmetric group S3 defined by, if you define the function, is to just define the permutation. Let's say this is 2, pi of 2 equals 3, pi of 3 equals 1. So this is a bijection. And we can write pi as like pi 1, pi 2, pi 3, which is pi 1 equals 2, is 3, and 1. So this one-line notation, and also in two-line notation, it will be 2, 3, 1. So you can think of this as a map sending this into this to this, and this to this, etc. So we can compose pi with itself. So this is pi squared. So what is the in two-line notation? So two-line notation is helpful if you want to understand I sends to what number. So if you apply pi, then pi will send 1 to 2, and then you have to apply pi again. So 1 gets sent to 2, and then 2 gets sent to 3, so 1 gets sent to 3. And 2 goes to 3, and then 3 goes to 1, so 2 goes to 1. 3 goes to 1, and 1 goes to 2, so 3 goes to 2, like that. So of course this in one-line notation you can also write this way, and etc. And an important notion is a cycle. A cycle of a permutation pi is a sequence a1 dot 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 ak, sequence of distinct integers, distinct let's say elements, such that if you apply pi to a1, you get a2. If you apply pi to a2, you get a3, etc. And if you apply pi to ak, you get a1 back. So it's like this goes to this goes to the next element, etc. And this goes back to 1. So that's if that's the case, then we say that this sequence is a cycle of pi. And as the name suggests, we will consider a1 cyclic shift to be the same, like aj dot 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 ak, a1 dot 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 ak j minus 1. So cyclic shift, if I cyclically shift the elements, they will all this cycle is considered to be the same as this cycle. Okay. Right. And so this, when you say cycle, it may mean several things. For example, a cycle of a permutation is a sequence like that, but we also say sometimes just this as a cycle without referring to any permutation. But that means this is a permutation in Sn that sends elements like this. Now let me write this in more details. So a cycle, say a row like a1 dot 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 ak is also considered as an element or as a permutation in Sn. Of course, if all the entries are less than or equal to n, in this way, such that so pi of I, we have to define what row of I is, and this will be say j plus 1. Okay, let me write this way. Row of ai equals ai plus 1, and the row of say r equals r, if r is different from all of these elements. And here of course I mean that ak plus 1 is a1. Okay, so it's a map from n to n. It's a bijection, so it's also you can think of this as a permutation. So when I say a cycle, it would mean either this or a cycle of a specific permutation, but the meaning must be clear from the context. All right. So this is called length, cycle of length k. So cycle of length, the length of a cycle means the number of elements in the cycle. Okay. So a transposition definition, a transposition By the way, we will see a lot of definitions today, yeah, and this will be useful, very useful in our lecture. So let's see. Our transposition is just a cycle of length 2. So any cycle of length 2 is called a transposition. So a transposition looks like, it looks something like this, I comma j, for different I and j, okay? And a simple transposition is a cycle of this form, I plus 1. So it's a transposition, it's called a simple transposition. Okay, and now let's see what happens. Pi 1 dot 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 pi n is a permutation in Sn, and tau is simple, just a transposition ij. And let's see what happens if we multiply pi and tau. So it's a permutation, it's a symmetric group, so you can multiply two elements. By the way, the symmetric group is not abelian, tau sigma may be different from sigma tau. So we have to consider pi tau. What happens? Let's see what happens, pi tau. So you see here, tau will only do something with I and j, and it remains other things just untouched, okay? So if you have, for instance, if you have one, let's say I is less than j, so everything else except the position I and j, this must be exactly the same as the original pi, right? So it's a pi 1, pi I minus 1, and pi I plus 1, pi j minus 1, pi j plus 1, pi n. But here, originally it was pi I, but now it's going to be pi j. This is pi I. So these two things are switched. Because this sends I to j, and then pi sends j to pi I. So, j to pi j. So this, as a whole, this will send pi to pi I to pi j. And so that means you change the two numbers in position I and j, okay? And if you change the order of the product, then it's not the same. And this is like pi, let me say it this way, with I and j interchanged. That means, in other words, if pi is like I and j, if their relative positions are like this, and then tau pi looks like ji. So only I and j are interchanged, but the remaining elements are just staying there. So is it different because what happens if we multiply, we apply this to k? If k is different from I and j, then this will not change. But if if pi something is I, then this will change I into j. So that's why we get these two changing. Okay. So you have to notice the difference between this and this. Okay. All right. And a nice theorem or proposition is that every permutation can be written as a product of distinct cycles, disjoint cycles. So let pi be an element, Sn. Yeah, I will sometimes write this Sn. Yeah, they mean the same. Then we can write pi as a product of some disjoint cycles, rho 1 dot 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 rho k, of course in Sn. We can always write a permutation as a product of disjoint cycle. So but it's not unique. There could be many different ways of doing this. Yeah, so let's see. And also, moreover, we can actually take these to be simple transposition. Let's write this way. Tau say R, where simple each tau I is simple. So in other words, we can write pi as this product of disjoint cycles, but we can also write pi as a product of simple transpositions. But of course here, they may not be disjoint. They may have several elements appearing more than once. Okay. Actually, let me prove this. I'm gonna give you just the idea. Just take k to be maybe k is not the right index. Let's say k equals 1 and m equals 1. And then you start with 1, and then see what happens if you apply pi to 1. So you have 1 here, and then you consider pi of 1. Okay? And then you consider applying pi one more time to this, and then pi like this. It's an infinite series, and we can define this infinite series, but of course, these are all elements in n. So eventually we have to have repetition. So at some point we have two integers appearing twice. So we can say this is, let me write this as m because I want to do with other integers as well. So this is equal to this for some, let's say I less than j. But if you apply a pi inverse, pi to the minus I, then you get pi to the 0th, which is the identity map. So this is m equals j minus I m. So that means we can find a smallest. We can find there is a smallest r greater than equal to, it could be 0. Sorry, it must be 1. Such that pi of r to the m is m. Okay? But that means this is a cycle. Cycle of length r minus 1. Sorry, length r. Cycle. Okay? Now you have found one cycle, and then just pick m as the smallest integer among the integers not in this cycle. And then you do the same thing, and then you will get another cycle, disjoint, and you can do this over and over, and at the end you will get all the cycles of pi, and then let's say this is rho 1, I repeat with m minimum element of n minus rho 1, let's say. This means you delete all the elements in rho 1. And then you do this over and over, then you get rho 2, and then etc. So that you get pi as a product of cycles like this. Okay. They are all disjoint. Why are they disjoint? Because if you have two cycles with a common element, they must be identical because one element completely determines the cycle. So, by the way, if you have disjoint cycles like this, as the product of this, the order doesn't matter. Two disjoint cycles commute. If you think about how the composition works then. So the order doesn't matter. Okay, so that proves the first statement. But what about the second? How can we write this as a simple transpositions? Let me just give you the idea for the second statement. What happens if you multiply? What happens if you multiply I plus 1 on the left? Simple transposition. That changes the pi I and pi I plus 1. So, is that right? You can interchange the two adjacent numbers. That means by doing this, you can kind of sort these integers into array into the identity permutation 1, 2, 3, dot, 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 n. So we can sort pi to 1, 2, dot, 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 n by successively interchanging adjacent numbers. But interchanging adjacent numbers corresponds to multiplying a simple transposition. So that means pi equals tau 1 dot, 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 tau r with simple transposition. So that's the proof, basically. And because of this proposition, we can always write permutation as a product of disjoint cycle. So we say it as a cycle notation. So in cycle notation, we write pi rho 1 dot, 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 rho k, where rho i's disjoint cycles. And with all, okay, so did I write the number of cycles? Oh no. So, and let me define it here. Cycle of pi is the number of all cycles in pi. So let me give you an example. So pi is 9518 26743, which is an element in S9. So in two-line notation, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9, 5, 1, 8, 2, 6, 7, 4, 3. So you can write this as a product of cycles. You can just find all the cycles. So to do that, let's begin with 1. 1 goes to what? 1 goes to 9. So we draw arrow like this. 1 goes to 9. And 9 goes to 3. And 3 goes to 1, back to 1. So we complete the cycle like this. And the remaining integers, the smallest, what is the smallest? 2. 2 goes to 5. 5 goes back to 2. And 4 goes to 8. 8 goes to 4. And 6 goes to itself. 7, like that. And I think that's it. So in cycle notation, it is like 1, 9, 3. We don't need a comma here. 2, 5, 4, 8, 6, and 9. So this is the cycle notation. And sometimes we omit the cycles of length 1 because they are basically just, they are really just identity. So sometimes we can write this. They are the same. But when we say usually cycle notation, we include all the integers there. So in this case, number of cycles of pi is 5 because there are 5 cycles of pi. Yeah, there is a special kind of permutation called an involution. A permutation pi is on involution if pi squared equals the identity. Identity means this identity map. And if you consider the cycle structure of pi, every cycle must be of length 1 or 2, because otherwise, if it's an involution, because otherwise, think about this. Pi squared equals identity means if you apply pi twice, every integer must be sent to itself. But if you have a cycle of length more than 2, then you can go twice and still you're not where you started. So every involution has cycles of length 1 or 2. So that means, and if you have a cycle of length 2, the orientation doesn't matter, because this goes to this goes to this, is really the same. But here, if you have a cycle, the orientation matters if the length is 3 or bigger, because this is different from this. But if you have a cycle of length 1 or 2, the orientation doesn't matter. So this, you can think of this as just a single point. You can think of this as connecting two dots like this. Then that's exactly a matching. So this bijection, there's a bijection, just a natural bijection between involutions on N and matchings. Not complete matchings, not necessarily matchings on N. So involutions are really matchings. They are really the same. All right. Now we're gonna define an important quantity called inversion. So pi is a permutation. An inversion of pi is a pair of integers I comma j such that I less than j but pi I greater than pi j. So in other words, an inversion is a pair that are out of order. So pi I is here, pi j is here because I is less than j. So, but the bigger one comes first. That's then ij is an inversion. So for example, maybe I can give you a. So what are the inversions? There are many, but let me find a few. 3, 5 is not an inversion because this is correct order, but this 4, 8 is an inversion because 8, 4 is out of order, and 4, 9 is an inversion because they are out of order, etc. All right. So the inversions are like that, and INV of pi is the number of inversions in pi. Okay. Yeah, maybe we can have just a simple example. Let's say pi equals, in two-line notation, let's just say 3, 1, 4, 2, 5, say. Then, what are the inversions? So 3, 1, 3, 2 are out of order. So 1, 2, 1, 4. And everything with 1 are in the correct order, and 4, 2. So 3, 4. And I think that's it. So is 3. Sometimes people define inversions like pair of pi I, pi j. It's just the values that are out of order. So, but this definition should be the same. An important feature about these inversions is that we can define the sign of a permutation using inversions. So the sign of a permutation pi is defined to be, I'm going to write SGN of pi minus 1 to the number of inversions. Okay? So for example, sign of the permutation 3, 1, 4 to 5 is minus 1 to the 3 equals minus 1. What is the sign of an identity permutation? It has no inversion, so minus 1 to the 0, so it's 1. So sign of the identity permutation is 1. Actually, there are several ways to define the sign. So maybe you have seen the definition of a sign somewhere else, and maybe you have seen something different. But they are all equivalent. There are many equivalent definitions of the sign. So we will see some of them. But let me first show you some lemmas before doing that. So pi is a permutation, and tau is a composition in Sn. And when you multiply permutation with a transposition, the cycle structure changes a little bit, but not too much. So number of cycles, especially, this is the same as the number of cycles of pi sigma, and this is equal to either cycle pi plus 1 or cycle pi minus 1 if I and j in the same cycle, different cycles. If the same cycle, of course, in pi. Okay, so let's prove this. I'm going to just show you just the idea. So let's suppose the first case, pi I and j in the same cycle. Then if you consider the cycle structure, it looks something like I goes to I and j in the same cycle. So we have something like that. But let me say A, this is B, C, and D, and something like that. Okay? We have a cycle structure like that. This is pi. Let's say this is one cycle in just a cycle of pi. And see what happens if you multiply ij, the transposition ij on the left. And what happens if you multiply ij? Then you get, so this means I goes to j, right? So if you consider this in pi row, say sigma, rho tau, you consider rho tau first. So I goes to j first. So I goes to j, but you now apply rho, so j goes to d. That means I goes to d, right? Why is the direction strange? So it's a counterclockwise direction. Okay, And j goes to I, so j goes to I, and then in row I goes to j, so j goes to b. So we have, at the beginning we have one cycle, but it's now split it into two. So we have one more cycle in this or in this, oh sorry, yeah, here. So it's going to be, the number of cycles will be increased by 1. But the other way is just this goes to this, so it's a number of cycles decreased by 1. So in other words, if you multiply a transposition, either you split a cycle or you merge two cycles, depending on whether these ij are in the same cycle or not. So in particular, if you multiply a single transposition, both on the left or right, I only proved this case, but this can be proved similarly. So in any case, if you multiply a transposition to the left or to the right, the number of cycles always decrease or increase by 1, so plus or minus 1. Okay? That's the important thing that we have to remember. And another lemma.
그러면은 같은 사이클 안에 있을 때가 사이클이 하나 더 들어가는 겁니까?
Oh yeah, that's right. So yeah, I think I made a mistake here. Yeah. Yeah. So if they are in the same, if they are in the same cycle, we have plus 1, and if they are in the different cycle, they merge, so number of cycles decrease by 1. So yeah, that's right. Yeah. All right, and for the next, let's look at the case simple where tau is a simple transposition. Then the sign of pi, if you multiply this, then it changes the sign. If you multiply a simple transposition, then sign changes. Actually, we can state this in a more general way, but I will only prove this because that's the simplest. So let's just consider, this is quite simple. If you look at let me just write this. I plus 1, you just interchange these two adjacent numbers. The other numbers stay the same. So what is the number of inversions? So number of inversions is the number of pairs of numbers that are out of order. So you choose, you look at two numbers and then check if this is out of order or not. And if you compare this and this permutation and this, the only difference is we interchange these two adjacent numbers. So the number of inversions, in other words, number of pairs out of order, that only changes if you consider the two numbers exactly this. Otherwise, for instance, if you consider this and this, their positions are like this, but their relative positions are still the same, so the number of inversions doesn't change. So number of inversions of pi tau is plus or minus the number of inversions, depending on whether this is Illian inversion or not. But we don't really care about the exact sign, but exact plus or minus, but because the sign is what we need, in any case, we always have the minus of this permutation sign. So this is true. So multiplying a simple transposition on the left, on the right, changes the sign. Actually, it's true if you multiply on the left, but we don't need that right now. So another lemma: if pi is a product of simple transpositions, then the sign is minus 1k. yeah, proof is not difficult. Sine of, we want to consider sine, but this is sine of tau 1 tau k. And we can say that, oh, there is an identity over here, because it doesn't matter. But whenever you have, okay, I think it's better if I use identity over here. Then you can move this outside, then multiply minus, right? So this is minus sine id k minus 1. So you do this, then you get minus 1 sine of k identity, but the sign of the identity is 1, so it's simple like that. And we showed that permutation can always be written as a product of simple transpositions, so we can always compute the sign in this way. And a nice corollary is that the sign is a multiplicative function. Like that. Because we can write pi as a simple product of simple transposition, and also this is a product of simple transposition, simple, and also then what is the sign of pi? Minus 1 to k, sign of sigma, minus 1 to r. But what about the sign of pi sigma? This is really the product of these two. So it's a product of k plus r simple transposition. So it's minus 1 to the k plus r. So that's the same as the product of this. So that's the proof. Okay? So this is a nice property. And now we can finally prove the equivalent definitions of the sign of a permutation. But let me do this in the next page. So proposition. Pi is a permutation in Sn. Then sign of pi. This is the definition, but let me write this just to compare other things. This is equal to minus 1 to the n minus the number of cycles of pi, and also equal to minus 1 to the number of even cycles. Okay. This is what we want to show, but in particular, if pi is a product of, let's say, k, where k, ti, each ti is a transposition, not necessarily a simple transposition, then the sign of pi equals minus 1 to the k. So, yeah, because if you know this, then this is a consequence, because even cycles, everything here is an even cycle. So the number of even cycles is t to the k. Okay, let's prove this. So this is the definition, so we don't have to prove this. So let's prove this first. For that, let's write this as a product of simple transpositions. Okay, and then we know that the sign of pi equals minus 1 to k, because we proved this. Number of simple minus 1 to the number of simple transpositions. This is what we showed. and also, since pi equals t1 dot 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 tk times the identity, what is the number of cycles of pi? So initially we have number of cycles of the identity, but we multiply a simple transposition. This is a transposition after all. So if you multiply this to this, you change the number of cycles by 1 or minus 1. And also you change this plus or minus 1, plus or minus 1. So that means you get this plus k or minus k, doesn't matter. Okay. But what is the number of cycles of the identity permutation? That's n. Every I is a cycle by itself. So it is minus 1 to n minus k, or n plus k, doesn't matter. That means minus 1 to the k is minus 1 to n minus cycles of pi. So this is equal to this, this is equal to this, so that's this. And what about even number of cycles? Okay. Yeah, so to prove the last one, let's say Ci be the number of cycles of length n, length I. All right? Then every integer must belong to exactly one cycle, and a cycle of length I has I integers, so this must be equal to 1 times C1, 2 times C2, plus dot 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 n times Cn. Because this cycle has cycle of length 1, there are this many cycles of length 1, then in total we have this many elements there. And there are C2 cycles of length 2, so in total they have these many integers, etc. So this is it follows from the definition. But what is C1 plus dot 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 Cn? It's a total number of cycles, so it's a cycle of pi. Right? So we already know that the sign is minus 1 to the n minus cycle of pi. So now we can just plug in these numbers. So minus 1 to 1 C1, 2 C2, minus C1 Cn. So we can rewrite this. So 0 times C1, 1 times C2, n minus 1 times Cn. So C2k has coefficient this, so it survives in the sign, but C2k plus 1 has sign, coefficient 2k, so minus 1 to this is just 1, so you can forget about this. So we only get even number of cycles of even length, and yeah, that's it. That's basically it. So that's number of even cycles. Okay. Yeah, I think maybe I can say a little more about this. Actually, this is not the cycle decomposition of pi. It's just one way of writing pi as a product of transposition. So I think a correct way to prove this is sign of pi. We use the multiplicative of the sign. Right? This is true. But the sign of a transposition is minus 1 because it has cycle of length, only one cycle of length 2, and the other cycles are or cycle of length 1. So the sign of a transposition is always -1. So yeah, I think this is the right way to prove this. Yeah. Okay, so we now have this several definition of the equivalent definition of the sign. This sign of a permutation will be very important when we study the determinant of a matrix, because the determinant of a matrix can be written as the sum of all permutations with a sign involved. So we will see that later. And now we can define Stirling number of the first kind, but we first define the signless number of the first kind, C and K. The signless Stirling number of the first kind is just the number of permutations on the set N with exactly K cycles. Okay, and the Stirling number of the first kind, the Stirling number of the first kind is, which we denote lowercase s and k. The capital S and k is the Stirling number of the second kind. And this has sign, so it's -1 to the n minus k, c and k. So the signless Stirling number of the first kind is the absolute value of the Stirling number of the first kind. And actually, you notice that this is the sign of any permutation with a K cycle, right? Because the sign of a permutation is n minus number of cycles. And there is a nice recurrence for the Stirling numbers of the first kind. For nk greater than or equal to 1, c and k equals c n minus 1 k minus 1 plus n minus 1 c n minus 1 k. This, but the proof is really similar to the proof of the recurrence for the Stirling number of the second kind. So just imagine that cycle of pi equals k. Suppose that the pi has k cycles. Then just focus on the number n. If the case 1, n itself is a cycle in pi, then except n, then the other part here will be c n minus 1 k minus 1. Except this, we have n minus 1 entries, integers, and we have k minus 1 cycles, so that as a whole we have k cycles. The case 2. Otherwise, and n is pointing to some number, right? So some number, say r, and it looks something like this. Maybe I can. So we have a bunch of other cycles like that. But then just consider this cycle. Just consider this cycle. And then together with all this. This is going to be c n minus 1 with k cycles, right? But we can obtain this by choosing the number that n is pointing. And there are n-1 possibilities to choose this number because this can point anything. And then you can just insert n there. So that's in total, we get n-1. So this is the number of ways to insert n into one of the n-1 possibilities. Okay, now let's see. Yeah, so we can prove things like this. A generating function for all c n k x to the k equals x sub n. K to the infinity, but it's actually up to n because otherwise it's 0. This is the folding factorial x sub n. Okay? And proof, probably the fastest proof would be induction using recursion. Right? You can just use this recursion and you can prove this quite easily. Right? So that's one way. But let me show you another proof, bijective proof. So actually, we can rewrite this this way. Equivalent form is that we consider all permutations of n x to the number of cycle. Cycle is x sub n. This is really the same as this, right? Because x to the k, the coefficient is the number of permutations with exactly k cycles, which is this. So they are the same. So we have this. There's a nice bijective proof of this. So let me give you a proof of this in the next page. Actually, we already have a proof, but let me prove this bijective proof. Bijective proof means we find a bijection, some kind of bijection that proves this identity like immediately. So to do that, I'm gonna, this is, oh, sorry, I think this is not correct. Sorry about that. Yeah, this is not correct. It's not a folding factorial, but actually it's a rising factorial. Yeah. Rising factorial like that. We will construct. We have an algorithm to construct a permutation. How do we construct an algorithm? How do we construct a permutation? We start from integer, smallest integer 1, and then make a cycle. And then once you have constructed a permutation in sk, let's say sk minus 1, add k into the picture of the cycle diagram, and there are two possibilities: create new cycle, new cycle, k like this, or insert k into let's say P4, let's say B4 I, where I is from 1 to k minus 1. That means we have already a I here, like that in the cycle, but I'm going to insert k like that, so that it goes like that. Just like the one that I showed you earlier. So in each stage, we have two choices, or several choices. Actually, we can do this, or we can do one of these. But that is exactly what we do when we expand this. This is x plus 1. X plus 2 is x plus 1 plus 1. X plus 1 plus 1 plus 1. X plus 1 plus ... 1. So if you have the kth factor, kth factor looks like this. So how do you expand the product of polynomials like this? You select one term in each factor, and then you multiply them all together. So in the kth factor, looks like this. So either you select this, or you select this, and etc. And selecting this corresponds to creating a new cycle. And selecting this corresponds to inserting k before 1. And selecting this corresponds to inserting k before 2, etc. So the way you expand this is exactly the same structure as the way we create a permutation. And this x really follows the number of cycles, because if you create a cycle, you multiply x. So that's basically the proof. So that's the bijective proof of this in words. Does this make sense? So in other words, the way, if you expand this, so for example, x plus 1, x plus 1 plus 1. This is x, first one, or x, let's say 1a, 1b, x, 1a, ab. So what I'm saying is each term here corresponds to exactly one permutation, and the term equals the power of x is the number of cycles of that permutation. So that's why these two quantities are exactly the same. So that we found a bijection between the all terms here and all terms in the expansion, and they are equal term by term. So that's why they are the same. So this is an example of a bijective proof of an identity like this. We just combine the two terms together, two sides together. And as a corollary, we have summation. The generating function for this Stirling number of the first kind. Now this is correct. And this is really, here we already know this. So change x to minus x and multiply -1 to n both sides, then we get exactly this. Just you can just do the computations, a simple computation. You see minus, and then these become folding factorial if you multiply -1 to the n. So that's exactly this. This is exactly this. Okay, so we have a nice. So now you may wonder why this is called the Stirling number of the first kind, and why the capital S is the Stirling number of the second kind. And there's a reason, because we have the duality like this. So we have a theorem like this, capital S, and choose k, x sub k equals x to the n. We proved this before using the number of functions, all functions from n to k and n to x. So, but if you look at these two carefully, you'll see that you can write down the matrix equation. You can make a matrix using, let's say, a small s. So nk greater than or equal to 0. So all is an infinite matrix. And then if you multiply, this is a infinite square matrix. This is now a x to the n. It's a column vector. So if you multiply these two, each entry must be this. So it's going to be this. So we get another vector like that. And same from the second identity, we get this matrix multiplied this and this. Okay. But if you look at this column vector, this is a sequence of polynomials, 1x, x squared, dot, dot, dot. So this is a basis of the space of the polynomials. So this is the basis. This is also a basis because each polynomial has degree n. So this is the change of basis matrix. So it must be invertible. So it's also invertible. So if this changes this basis into this, and if this does the other way around, that means these two are inverses of each other. So theorem or proposition S and K equals or S and K equals the identity matrix. Or if you look at the entry n comma m entry equivalently, you can also write, let me just say for all k, S n k small n k m equals delta m n. They are all actually they are all equivalent. Yeah. And actually, if you look at this has some combinatorial meaning, number of set partitions of n into k blocks. This has combinatorial meaning with some signs involved. So there is a way to prove this directly using by constructing a sign reverse involution. Also for this, yeah, but yeah, there's a kind of standard well-known result, but I'm not gonna go into the details. But if you are interested, you can try to prove this using sign reverse involutions. Yeah. Okay, so we have developed more or less what we need to study orthogonal polynomials combinatorially. So from the next lecture, we will really go back to orthogonal polynomials and then study them combinatorially. Okay. All right, then I'll stop here. Thank you.